Um, so the title of this talk reads, Networking and Information Theory, a Still Unconsummated Union. For those of you who are not aware of the origin of these names, there is a famous paper by Professor Hayek and Anthony Ephremidis, which reads Networks and Information Theory, an Unconsummated Union. That was published in 1998, and a decade or more has passed since that survey. So this talk provides a quick overview of what happened in the last decade in the intersection of these two areas. Okay, so first I'll give a quick overview of this intersection between these areas, and then next we'll go into the networking approaches to the union between these areas, then the information theoretic approaches, and then we'll see some hybrid approaches in this intersection. Okay, so this talk is going to be about a very zoomed out picture, and to start with, let's place wireless communication in the context of wearable inventions, as I call it. So there are very few things that you carry daily. There's clothes, there's money, there's time, and then there's a cell phone. So it has become a fundamental part of our society, and maybe biometrics is coming in, and maybe everybody will have an embeddable biometric in the future. But sticking to the present, it's going to be wireless communication, and in particular, wireless networking, as we'll see as it goes on. Okay, so what is networking? Networking is basically the study of protocols and schemes for communication between agents that are decentralized in space. So the goal could be anything that varies from maximizing network utility, or the long-term revenue, or the satisfaction, or the stock price of the company which is operating the network. And there are some constraints. There are channel constraints, there are quality of service constraints. So, okay, so this is the problem. So how did they solve it in the last few years? Basically, we have a layered approach where the whole process of networking has been divided into smaller layers, where each layer takes certain parameters from the layer above and in turn provides some guarantees to the layer above. In particular, the most used model is this particular layering of application layer. I have not shown it here. Application layer, transport, networking, medium access, and physical. Physical layer basically deals with the channel uncertainty, or channel noise, as we can call it. The medium access is particular to the wireless medium. How do you share the common resource between the various contending users? And then there's a networking or a routing layer, which tells you how to route information across the network. And then there's a transport layer, which does congestion and error control. Okay, so that's a quick overview of networking. So what is information theory? Information theory, for our purposes here, would be the study of fundamental limits on reliably communicating and compressing information. In particular, we'll be focusing on communicating information. Of course, there are applications of information theory beyond just this limited definition, but for this talk, we'll stick to this. Okay, so it started with the study of point-to-point communications, where there's a single transmitter, a single receiver, no other person exists in the universe. I want to transmit to that other person. How do you do it? What is the maximum rate? What constraints do the channel place on you? That is information theory, essentially. And it has been later extended to multi-user networks. We'll see a little bit about it later. Okay, so what is this union between networking and information theory? In the time between 1950 and 2000, which is the starting phase of both networking and information theory, the networking theorists were essentially interested in studying wireline networking, aspects of queuing, how do you route information on a wireline network, and so on. Whereas the people in the information theory literature are mainly focused on understanding point-to-point wireless communication. How do you communicate information via a wireless medium? The major success story of networking in this era was the internet, whereas the major success story in information theory was cellular communication, the use of turbo codes, convolutional codes, channel diversity, and channel capacity in wireless communication. However, in the last 10 years, a more recent area has emerged, which is very much in the intersection of these two, which is wireless networks. What is an ad hoc network? Ad hoc network is basically an infrastructure-less network where users are highly decentralized and they want to communicate with each other, but in the absence of any infrastructure. So these networks pose significantly different issues than the wireline networks that were studied earlier on. Okay. So let's see. So these are the 4 layers that I initially talked about. Let's see what the union is all about. From an information theorist's perspective, he started out with the physical layer, just the point-to-point communication. And he takes a bottom-up approach, trying to integrate more and more of the network aspects into his physical layer viewpoint. Whereas the network theorist started out with the higher layers of congestion control, routing, and scheduling, and now he's faced with a new channel, the wireless channel, and how does he take that into account into design of the network? So the network theorist is a top-down approach, whereas the information theorist takes a bottom-up approach. So this is a conceptual abstraction. Of course, there's a significant overlap between these two communities. Okay, so let's start with looking at the information theoretic approaches to this union. Okay, so the information theorist's answer to this integration was network information theory. As the name rightly points out, it's really an intersection between these two areas. So what is the holy grail? What are they trying to answer in this area? Suppose you have a set of n agents, and there is a certain way in which the n agents' transmissions and their receptions are linked with each other based on a certain channel transition probability. What are the rates? So it should be R1 to Rn choose 2. Anybody could communicate with anybody, and this region is what they're interested in, given this channel transition probability. And how do you achieve this region in terms of what functions to use and how do you communicate to achieve any point in this region? However, even supposing somebody is going to solve this problem exactly, there are certain cons to this model. Let's look at it right away. It does not model the cost of decentralized actions. Normally you assume that everybody knows the channels, everybody is coordinating with each other, everybody is cooperating, they can design their code books jointly, they know how many other users are present, they know what rates they're going to use. However, several of those assumptions are going to break down when you take a decentralized approach. And also it does not matter, it is hard to capture feedback and asynchronism, while it can be done to a limited extent. Okay, so let's see what the progress has been in this area so far. So first, as you all know, the breakthrough paper by Shannon in 1948 found the capacity of the point-to-point channel. And the point-to-point channel just deals with the physical layer. Later, the multi-user aspects were incorporated into it. And if you take the multiple access channel, which is an uplink channel, where there are many users trying to contend for a single base station, the multiple access channel is therefore having the aspects of both the physical layer of communication and of scheduling, even though the aspects are mixed together in a inseparable manner. So the multiple access channel capacity was found in 1971, and similarly the dual of this, where there is a single source transmitting to 2 destinations. How do you schedule and how do you do the physical layer, or how do you design them jointly? This is the broadcast channel, and this was solved for the Gaussian case in 1973, and for the Gaussian case with multiple antennas in 2006. Then again, this is a slightly harder problem, where you have 2 sources, 2 destinations, and each source wants to talk to its corresponding destination. What is the capacity region for this? This was open for a long time, and recently there was some progress in this area in terms of approximating the capacity rather than getting the exact capacity. So again, this deals only with 2 layers, scheduling and physical layers. There is no routing really here, because they're all point-to-point or single hop communication. So the Gaussian relay channel, where there's a single source, single destination, 1 or multiple relays to help communicate between the source and the destination, this incorporates really all 3 layers of physical, scheduling, and routing, because now you need to think about how information propagates through the network and how to get the maximum amount of information possible to the sink. Okay, so this has been the bottom-up integration that I've been talking about, and this is till 2007, this is how far they've reached. However, these are very specific results for single source, single destination, and the multiple source, multiple destination problem is famously open. Okay, so what led to these? As you saw in these last 2 slides, the relay and the interference channel were solved very recently, and what led to the solutions of these? So the interference and relay channel were basically solved using a deterministic approach. What is a deterministic approach? There are two main issues in wireless communication. One is the noise that you encounter when you transmit, and the other is the interference caused by other users. The interference caused by other users is not noise because they're structured in a certain manner. So the deterministic approach is basically just abstracting away the noise, saying that, okay, so if let's say the noise variance is 1, let's quantize to integer level. And now if I transmit anything, I'm just going to receive the integer part of it. So this is a deterministic approach to this stochastic problem where there is the effect of noise. And this is somewhat at a conceptual level similar to the fluid model used for approximating stochastic systems. As you can imagine, this kind of gives the limiting behavior of the original system as the SNR becomes very large, because the noise becomes smaller and smaller, the system is already becoming deterministic. So based on intuition derived from the deterministic networks, the problems of relay and interference channels were solved recently. However, a general result connecting deterministic and original network for the original Gaussian network and the deterministic network is an open problem, and some progress has been made in this direction by modifying the deterministic network to a different manner by Anand and Kumari. Okay, so so that was the information theorist approach towards merging the aspects of information theory and networking. Now let's look at the network theorist approach. So the network theorist started with the higher layers and tries to incorporate the new properties of the physical layer into this. So the way they do it is by breaking down the barriers of layering, by jointly designing various layers. And one example could be if you could design your routing and scheduling layers jointly. So there are two issues here. Where do you layer? Where exactly do you draw the boundary between this is the first layer and this is the second layer? And if so, once you have found that, what information do you pass across these adjacent layers? So, so the second issue is equally important, because if you were to pass all your information down to the next layer and down to the next layer and so on, then really there's no layering. You want to keep the information interfaces as minimal as possible. So these are the two issues. And one of the ways to understand this has been the network utility maximization framework, where the viewpoint is that the network is basically a utility maximizer. The network tries to maximize a certain utility, which could basically be the sum of utilities of the various users, it could be the lifetime of the network or anything. And then there are capacity and QoS constraints, whether you have to schedule within a given time or whether you have to provide a certain probability of error guarantee. So the viewpoint here has been to take this huge optimization problem. Now the whole network is an optimizer. Take this huge optimization problem and try to see if this problem breaks down into smaller units, which can be more easily dealt with. And you can think of these smaller problems as basically the layers. So the approach here has been a little bit of reverse engineering, in the sense that you know that these are the layers. Try to find a certain utility function and write the constraints in a certain way so that the problem breaks down into the layers that you already designed. However, this can give you a huge amount of intuition as to how to better design these layers. So that has been kind of the the network theorist approach to this union. So till now, NUM covers several aspects of congestion control, routing, and scheduling. However, it does not fully utilize all the properties of the physical layer. To that extent, this picture is incomplete. There could be a lot more things that could be done. For example, if you have a relay channel, there is a lot of physical layer aspects that need to be taken into account when you do routing, because you just don't route. You have to route real information. You don't route just packets. You route information. So that is as far as this approach goes. However, there have been several interesting approaches in the intersection of these two areas, and they're really hybrid approaches. Okay. So the most famous of them being the scaling law approach, where if you have set of n nodes scattered uniformly in a unit circle. And suppose you assume that you're going to do just multi-hop routing and treat interference as noise, which is the limitation of current technology. You ask what is the symmetric rate or the sum rate that can be obtained in such a network. And even though the problem of solving this exactly is really hard, you can obtain the scaling behavior of this as the number of nodes becomes larger and larger. Again, if you look at this, this incorporates 3 layers of routing, scheduling, and the physical layer, because it's the physical layer that defines this, these parameters of treating interference as noise and the multi-hop routing, and the scheduling because you have to determine which person transmits when, and there is a routing layer involved here because it's essentially multi-hop routing. So this shifted the focus from exact and intractable analysis to asymptotic and tractable analysis. So there have been several refinements to this approach. So can you extend this framework to incorporate more general communication schemes? Like, suppose you allow any possible communication scheme, then one of the results has been that in a dense network, hierarchical communication architectures are optimal. So what is a hierarchical communication architecture? Suppose you divide the network into a series of clusters. Now, so basically the scaling laws just gives you architectural insights into how to design the network. They don't really tell you which scheme is exactly optimal, but they tell you architectural insights. For example, the hierarchical cooperation is basically you divide the network into clusters and of hierarchies, and at each hierarchy a cluster communicates to other clusters. If all nodes inside a cluster cooperate to communicate to other nodes in other clusters in the same way at higher and higher levels. So these kind of architectural insights can be useful when designing networks. And of course, there have been more realistic channel models than the ones initially proposed. So they show some interesting regimes of operation of network. In particular, two very interesting operating regimes. One is the power limited operating regime, where if you have a network, you have enough power to scream from one end of the network to the other. So in this case, you're really not limited by your power, but you cannot scream. Suppose you have a power limited regime, then you cannot scream from one end of the network to the other. So here you're limited, how much information you can transmit is limited by how much power you have. Whereas the other end is the interference limited regime, where you can scream all the way you want from one end of the network to the other, but the others are going to scream as well. So which means you can still get drowned out. So these are two regimes. One is the power limited and the interference limited. And this can give you high-level insights into how to design the network. So you look at a network and say if it's in either of these regimes or somewhere in between, then you think about how to design schemes. And one more interesting viewpoint here has been to integrate physical laws of electromagnetic propagation into the information theoretic approach. And this has been, again, a recent work by Francis Ketty et al. And this suggests that the original scaling behavior of order 1 over root n is in fact optimal. Okay, so now let's look at another hybrid approach, which is network coding. So network coding is a very interesting hybrid approach because it really doesn't involve cross-layer design. As most other schemes involve cross-layer design, this doesn't really involve cross-layer design. This is just a purely routing phenomenon. Here's what happens. So basically, when you're sitting at a router, you get some information from all the incoming nodes, and you have to route them across to one of the outgoing links. This has been the prevailing viewpoint. But then, as our late Professor Cotter put it, bits are not cars. You don't need to route them on certain highways. You could mix them and merge them in ways which can be very beneficial. So the routers can really transmit any function of the incoming information. So the most famous result in this literature has been the one of multicasting, where a single source wants to transmit the same information to several destinations. And the optimal scheme here turns out to be to transmit random linear combination of all packets that you receive, treating them as elements over a certain finite field. And the proof of this is using very standard information theory machinery. So then why did it take till 2000 to solve this problem? setting up of this problem was the hard part, because so this was solved essentially by information theorists, at least initially. The information theorists used to operating at the physical layer. And suddenly, there was a paradigm shift in order to zoom back and say, okay, let's go to the networking layer and think about how information theory can be used there. That's why it was a very, it took a long time to get to this result. Okay, so let's go to the next one, which is fountain codes. So the network coding idea that we got initially has several applications. In fact, it was found to have applications in queuing and so on. So if some of you are wondering why the Velociraptor is sitting here, some of the fountain codes are called raptor codes. And this is the picture he uses in the fountain code slide. Okay, so what is the problem set up here? Suppose you have a satellite and you want to transmit a movie to various users who are listening to you, but they tune in asynchronously. So each one can tune in and listen to your movie at any given time. So and suppose your physical layer is a broadcast erasure channel, which means you put out some packets and all of you receive those packets, but with some erasure probability, which means the packet can get erased at some probability. So there are two questions now. Which packet to transmit at any given time, which is one of scheduling. And the other question is the physical layer question. How do you protect the packets against erasures? So now these are two distinct questions. However, if you look at them from a unified viewpoint, as they did in this approach, you get this fountain codes, which is basically to transmit a random linear combination of the packets that you have at any given time. And when a user tunes in, he receives as many linear combinations as he needs to decode the information, and then moves on. So this scheme is simultaneously optimal for all users, because each one just receives as much information as he needs in order to decode the information. So if you have a very good channel, you're going to start seeing the movie really soon. If you have a bad channel, then you have to wait for a long time before you can start seeing it. Okay. Okay, so the next approach we're going to see here is again one of mixing scheduling and the physical layer. This is opportunistic communication. So what is opportunistic communication? It's again the setup is the same. You have a downlink, but with fading channels now. So and suppose your objective is to maximize the sum throughput of the network. This is the total amount of information that you transmit to all the users. You just schedule to the user with the best possible channel state at a given time, because that is going to give you the maximum rate at any given time, and therefore the best sum throughput. However, so this is interesting for a certain reason, because this leverages channel variation. Channel variation was traditionally thought to be bad, because if the channel is varying really up and down, you can be in a really bad state and not get any information across. However, the viewpoint in opportunistic communication is that if there are many users, at least one of them is going to have a very good channel at a given time, and therefore the sum throughput can be better than if you didn't have fading. Okay, so this illustrates another very important point. So here we, as you can see, it's basically a joint scheduling and physical layer approach. The goals of a layer can differ dramatically depending on whether it's a cross layer or a layered approach. So what do I mean by that? Suppose you did not have opportunistic scheduling. Suppose the physical layer were to provide certain guarantees to the layer above, to the scheduling layer. Then the physical layer would say, okay, let me give you the maximum possible reliability, which means I'll use diversity to make sure that my channel is more or less constant at all possible times. Sorry. Without opportunistic scheduling, so this is what you would be doing. You would, in fact, make your channel as constant as possible. However, with opportunistic scheduling, you would, in fact, induce artificial variations to make sure your channel varies as fast as possible. So this illustrates that the cross-layer approach can very much vary the purpose of each layer. Okay, so let's look at one new problem before we wind up. Suppose you again look at joint scheduling and physical layer approach. But instead of looking at the downlink, suppose you look at the uplink. So uplink is basically multiple users who want to transmit to a single destination. Okay, let's look at two different formulations for this problem. First, a network theorist view. As usual, the network theorist takes a top-down view. So the top-down view here is there is only scheduling and physical layers. So let's go to the scheduling layer. And what is the result that we know? We know results on distributed CSMA. CSMA is carrier sense multiple access. So how do you do scheduling in a distributed manner? Those results already exist. However, they do not take the full aspects of the physical layer into consideration. They treat the physical layer as though they were a collision channel, which means if two of them transmit simultaneously, you're going to lose your packet. So now the network theorist's natural question is, how do you perform distributed CSMA in the presence of Gaussian channels? As far as I know, there has not been any solution to this. Okay, so what does the information theorist do? He says, okay, let me look at this channel. This is basically a multiple access channel. And in this multiple access channel, I already have a capacity result. But then I did not take into account the distributed nature of this problem fully, which means I assumed that I know how many other users exist, what rates they're going to be transmitting, and so on. Now the natural question is, what capacity theorems can be proved when users do not know how many other people are present? Recently, an approximation result was obtained for this by Minero, Francischetti, and Say, 2010. Okay, so let me wind up with just a couple more examples. One is the cognitive radio. So this is just to illustrate that this particular division of layers is not holy. In fact, you could have a spectrum layer above, which basically decides who transmits at what spectrum, and you could integrate that spectrum layer with the physical layer based on sensing. So the person senses which channels are free, and then tells the physical layer senses which channels are free, tells the spectrum layer, okay, this channel is free, and the spectrum layer instructs all the other layers to operate on this new frequency time plane. That's cognitive radio as cross-layer design. Similarly, the packets with deadlines. So packet with deadlines is basically the application layer is telling you, okay, this packet will expire in a few milliseconds. And now, can you use this information to design your congestion control or your scheduling or your routing? So there has been some recent work on this as well. Okay, so it's time to conclude my talk. So the holy grail of this union is not as clearly statable as we would like it to be, or at least not to me. However, lots of progress has been made in integrating various aspects of networks and information theory. And techniques from one can be used in other. For example, the deterministic models, basically, you can say it's inspired from fluid models. And the random coding from information theory in networks to do queuing, for example. Several interesting questions can be posed in this. And this is since it's a CSL student conference, there is a poster outside somebody's room in CSL. It says all models are wrong, some are useful. And a student wrote, some are just plain cute. Thank you. I'll be happy to take questions. Mm-hmm.
The view is still communicating bits from here to there.
Mm-hmm.
And I think going forward, what you want to think about is what do you do with these bits? The bits are not just end in themselves. You're computing on that, right?
Mm-hmm.
So I think it's really computation and communication together.
Mm-hmm.
And of course, there is work on that as well. But why stop?
Yeah.
Go one more layer up.
Yeah, definitely. That is one thing that can be integrated. It's not really, I mean, I'm just saying that this layering that you've been given is not holy. You could have something else that goes on, either in between or above or below. So thinking of spectrum as a layer above everything else is basically because everything else has to operate in a particular spectrum. And that information comes from top down. And the spectrum layer says, okay, all of you operate on this frequency, this time scale. And then everybody else has to shift their operation into that domain. That's why I put it there. I mean, but that's just to say that this is not really God-given.
Okay. Thank you very much.